All right, in this last video in 13.7, we'll look at question number 7, which says to find an equation of the tangent plane to the surface 3x squared minus 4xy plus z squared is equal to 0 at the point 1, 1, 1. Okay, so up at the top here I have a general formula which is going to tell us how to find the tangent plane to any implicitly defined surface. So notice in this equation here I don't have z solved for, and this is the same kind of thing that we saw in the last video where we found the tangent plane to a sphere. And so if I want to find the tangent plane to a surface like this at a certain point, well, I can just apply this result. But where is this coming from? Well, the thing to notice here is that the coefficients of x minus x naught, y minus y naught, and z minus z naught are really the components of the gradient vector of this function f evaluated at our point P. And where's that coming from? Well, that's coming from the theorem that we stated in the last video that said that the gradient vector at a certain point was perpendicular to the level surface for this function f that passes through that point. So here in this picture off to the side, okay, we're going to think about our given surface as a level surface of this function f, okay? And if I'm looking at, say, this point P on our surface, then that theorem says that the gradient vector at P will be perpendicular to our surface here. And if it's perpendicular to our surface, then it'll be perpendicular to this tangent plane at P, or that passes through P as well. Okay, so this is the gradient of this function f evaluated at our point P. Okay, so what exactly is this function f if I'm just given a surface equation like this, right? Well, the idea is if I just take this thing on the left-hand side and say, okay, this is my f of x, y, z, which would be 3x squared minus 4xy plus z squared, okay, then our surface, this is really the key insight, is just a level surface of this function f. It happens to be the level surface when I set this right-hand side equal to 0. Okay, if I set that right-hand side equal to other values, right, that's where all these other surfaces are going to come from, right? So ours is just one of many in this family of level surfaces. Okay, so then applying this result up here, well, in order to do that, I need to know what the gradient vector is. So let's do that. So the gradient at any point would be what? Well, if this is our f, the x derivative would be 6x minus 4y. The y derivative would be minus 4x, and the z derivative would be 2z. So then if I evaluate this gradient at our point, whose coordinates are 1, 1, 1, I'm going to get the vector 2, negative 4, 2. Okay? And as we were saying over here, this gradient will serve as a normal vector for the tangent plane whose equation we're looking to find. Okay. So now, to finish, right, I'll go ahead and write the tangent plane equation right here. Okay, I'm going to take the I component of the normal vector, so that'd be 2, times x minus the x coordinate of our point P, which is 1. Then minus 4, that's the j component of our normal vector, times y minus the y component of our point, y coordinate of our point, so that'd be also 1. And then lastly, plus 2 times z minus the z coordinate of our point, which is also 1, and that's going to equal 0. I'll go ahead and clean that up a little bit by just multiplying stuff out. I'll get 2x minus 4y plus 2z is equal to what? Well, this would be minus 2 plus 4, so that'd be 2, and then minus 2, so it'd be 0. And I'll go ahead and divide through by 2 as well, so it's a little bit cleaner. But there would be our tangent plane equation. All right, that's going to do it for this video as well as section 13.7. See ya.